Okay, the theorem. So let me. One naive version of the theorem is the following. So theorem, not too small. Okay, theorem is that naive version, as we were saying. Let me remind you, is that every finite abelian group is a finite direct product of finite cyclic groups. Okay, this is a very naive version. So, as we were saying yesterday, that the simplest kind of finite abelian groups are cyclic groups, finite cyclic groups of the form Z mod NZ, right? And then you have this notion of direct sum. You can take Z mod one cyclic group of order N1 and another one of order N2, and you could take a direct sum. And this will give you another finite abelian group, may or may not be cyclic, depends on how N1 is related to N2. But the point is, if I take any abelian whatsoever, then this is isomorphic to, okay, let me state it in these terms. Suppose M, N, let's say N, M, and M prime. Now, I hope the question is clear. I mean, this is a question in algebra, right? If you have an isomorphism, two things could become isomorphic after I add the same thing to both of them, but maybe they may or may not be isomorphic to begin with. But does this happen with finite abelian groups is the question. And okay, let me not tell you the answer. It's a good question if you don't know the answer to work it out. So the upshot is that this problem reduces to the case when N is cyclic, because you can assume by the structure theorem that N is a finite direct sum of finite cyclic groups. And so it follows. So if N is a finite direct sum of finite cyclic groups, say N1 and 1Z plus dot 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 plus Z NKZ plus M is isomorphic to the same thing, M prime. And if you can cancel, if it is, suppose I know it's true for cyclic, then I can start canceling them one by one, right? And then I'll come down to M is isomorphic to M prime. I mean, so the point is that if this is true for N cyclic, then that's good enough. So this is it's already useful in answering such problems to reduce to the case when N is a finite cyclic group. Okay. Now let's so last time we talked about the Chinese remainder theorem. So let me tell you what it is. Remind you what it is. Let A be a commutative ring with an entity, and one AN be pairwise co-maximal ideals. Then, as we saw last time, the intersection is the product. Okay, and that's one statement. But the second, perhaps even more important statement is that's only the build up towards this. So if I take the product now, which is the same as the intersection, and this is isomorphic to A mod A1 cross A mod A2 cross A mod AN. Okay, this is the statement of Chinese remainder theorem, and let's we're going to prove this now. But let's see, before even proving that, how we want to apply this. The way we want to apply this is the following. So we want to get from this some statement about finite abelian groups, and for that, let me remind you what we did yesterday. So given a finite abelian group, M, there exists D bigger than 0 integer such that dm is equal to 0. Okay, so in other words, thus M is a module. M is a Z mod dz module. Since D annihilates M, the structure of M as a Z module goes down to Z mod dz. Okay? This is easy to check because if two things differ by D, then they act the same way because D acts like 0. Okay. And so now we apply the Chinese remainder theorem. Okay, maybe I should. This is not. So Z mod dz. So I write this D as P1 to the R1, P2 to the R2, dot 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 Pk to the Rk by Euclid's division algorithm. Sorry, what am I saying? That's not correct. Yeah, by the fundamental theorem of arithmetic, right? And then these are pairwise co-maximal, right? Because well, we are over the integers. So now by the Euclid's division algorithm, you know that if I have A comma B is equal to 1, I mean, this has two meanings. One is that the GCD is 1. That is one meaning. And the second meaning is that A and B generate the unit ideal. Okay, so so it need not be true over general rings that two things that are relatively prime. That's what GCD means. GCD equals 1 means. They need not generate the unit ideal. For example, you could take the polynomial ring in two variables, and you could just consider the two variables x and y. They have no common factor, but they do not generate the unit ideal. However, over the integers, it's true that if two things have no GCD, then they generate the unit ideal. That follows from Euclid's division algorithm. That tells you how to compute the GCD. Okay, so what you do is you take the larger of these two numbers and subtract from it the smaller of the two numbers, right? And keep going, repeat this process until you get zero. And the one step before you get zero, what was there, that is the GCD. And so if you sort of unwind this, go backwards, you see that they do exist. If this is true, if the GCD is 1, if A and B, if the GCD of A and B is 1, then there exists x comma y such that xa plus yb is equal to 1. So these are integers. Okay. So that's what. Co-prime implies co-maximal. That is the property in integers. So these are, for the Chinese remainder theorem, we need that they're co-maximal. So what we get is that this is isomorphic to Z mod P1 R1 cross Z, like this, Z mod PK RK Z. Okay. Now, this is how we will use the Chinese remainder theorem. So our, M, which was finite abelian group, remember, and you fix D, some large enough integer. I shouldn't say large enough integer. I should say some suitable integer, maybe large, such that dm is equal to 0. Okay. And then you do this, right? And then what you can do is observe the following, that these now give you ideals in, so Z mod P1 to the R1 Z is you can think of this rather cross 0, cross 0, cross 0. So if I take other components to be 0, this is an ideal. So let me call this A1, right? That's an ideal here. That's an ideal in Z mod DZ. This similarly is the kth ideal. So that is 0 cross 0 cross 0 cross Z mod PK to the RKZ. Let's call that the akth ideal, and so on. There is a second A2, A3, A4, and so on. So the properties of these ideals are such that, just rewriting this, is that our Z mod DZ, right, is a sum of these ideals. Right? And so you can actually write this. So I want to do more. Let's observe the following. This has a rather beautiful structure. So by the Chinese remainder theorem, which I remember we haven't proved it, yet, but never mind, we'll use it before we prove it. So, so what it gives you is this. So E1 be the element corresponding to 1, 0, 0, and so on. K, the element corresponding to 0, 0, 0, 1. Okay, and then what you see here on this side is that these are idempotent. So what you get is E1 square is equal to E1, EK square equal to EK, right? And moreover, you have E 1 ei ej equal to 0 for all I not equal to j, right? And moreover, 1 is equal to e1 plus e2 plus ek, because the identity in this ring is just 1 plus 1 plus 1 plus 1. Okay, and that should correspond to the identity here, which is 1, because this is a ring homomorphism. Ring homomorphism respects identity. So you have this. So you have these idempotents, and so you can define. So you start with your M, right? This finite abelian group, and then now E1, E2, Ek are elements of this Z mod dz, and I can think of E1M, E2M, Ekm. Now these are submodules of M, and we have actually this. Now this is very easy to prove. For example, you give me an M, how do I write it like this? Well, that is just follows from this. Multiply by M, get M is equal to E1M plus E2M plus Ekm, right? And so that's obvious. Why is this a direct sum? That follows from this, right? And so on, right? So this is very easy to prove. And so what we do get is that this is a module. So what was this? So remember, this is in here, right? So the E1M will become a module over Z mod P1 to the R1Z. Because if you wish, it killed by all the E2, Ek. So all these will act as 0. So I can go modulo that, because those belong in the annihilator, and so I get a modulo over this. Okay. This, and this is a modulo of this. Okay. So okay, so let me make some comments here. So this follows from the Chinese remainder theorem, right? So these are called so E1M and Ekm are called the primary components of M. And E1M or EIM is, if you want to be more precise, this is the PI primary component of it. And this decomposition here, let me use this color. This decomposition here, you can call that the primary decomposition theorem. So this just follows from the Chinese remainder theorem. Okay, let me observe a few more points here. So there are various ways of looking at this. So let me, I'm sure many in the audience will be familiar with some concepts in algebra. So M is a finite abelian group. So it's obvious that it is a Noetherian module. Right, it's both. Matter is both Artinian and Noetherian. It's what is called a finite length module. Okay, so what that means is any chain of submodules in M stabilizes. So if I look at 0 colon, suppose so M is a Noetherian module, and fix a prime P. Okay, and then I look at what is killed by P in M. Okay, so what does this mean? This means 0 colon M. And if I have an integer A here, this just means all M in M such that AM equal to 0. This is a submodule. It is those elements killed by A. That's obvious, because if P kills something, then P squared definitely kills it. No question. And then 0 colon P cubed M and so on. So this stabilizes by the Noetherian condition. And what value does it stabilize to? Well, so here is an exercise to prove. So this stabilizes. The stable value of this is precisely the P primary component of M. Okay, so if P is one of these primes, then it has a non-trivial P primary component. If it is not, then the P primary component is just 0. That's what it means. So M has a non-trivial P primary component if and only if P is P1 or ... P is equal to Pk. If it is one of these, that has a non-trivial P primary component. If it is not one of these, then this actually is 0 always. That's one statement. Okay, it's a good exercise to do. Okay, let me also relate it to something else, right? Okay, so so we know Celo's theorems, right? We know Celo's theorems, and so the P primary component. So this is also, let's take this as an exercise. The P primary component of M is precisely the P Celo subgroup, the P Celo subgroup of M. Now, why am I saying the P Celo subgroup? Remember, we're in an abelian group, so any subgroup is normal, right? And we know that all P Celo subgroups are conjugate to each other. But here, conjugation doesn't do anything to a subgroup. So there is a unique, in any abelian group, there is a unique P Celo subgroup. And it is, this P primary component is nothing but the P Celo subgroup. So I hope this connects this up with various concepts in module theory, in Noetherian modules, and this is a standard kind of ascending chain that one considers. This is something in P Celo theory. There is something little more to add here. So if you know what the definition means, if you have an nilpotent, okay, so let me by P of M, okay, then the primary decomposition theorem says, okay, once again, I'll repeat here. So what's our hypothesis here? Let's see if, no, that's not good. Let me use this color. Okay. D is such that dm is 0. M is finite abelian group. That's our notation. And you have D is equal to P1 to the R1, P2 to the R2, K to the RK. That's your decomposition into primes, into a product of primes of D. And then we saw that this E1M was the P1 primary component of M, and so on. So this P1 of is E1 of M. That's what E1 is as above. Is the idempotent. This is the idempotent corresponding to 1, 0, 0, 0, and so on. Right? So this is the P1 primary component of M. P2 primary component of M would be and so on. So let us denote the P primary component of by Pm. So what we have is M. Now let's come back here. M is P1M direct sum Pkm. It's a sum of its primary components. Okay. Now what have we attained by doing this? Now notice that this is a module over Z mod P1 to the R1Z. Right? Okay. So now we are reduced to, to understand the structure of M, I'm reduced to understanding the structure of modules over Z mod P1 to the R1Z. This one will be Z mod Pk to the Rkz. So I can now assume that whatever I have here is scaled by P1 to the R1. In other words, this D I can assume to be a prime power for this module. So from a general D, we are down to the prime power case. Okay, that is the advantage of this primary decomposition to the RZ, let me call it, module. This is the question. Right, because we are down to this case where this is filled by a prime power. So of course here I am assuming that P is prime. So the assumption is that P is prime and R is some integer bigger than 1, let me say. If R equal to 0, then of course it is a zero ring. So that's not interesting. So this is the question that we are reduced to. Okay, and what is the answer here? Right. So the answer here is the following. So let me tell you the theorem, which will give us the answer here. So there, given finite Z mod P to the RZ module, there exists integers or what to say, non-negative integers. Let's say T1, so T sub R, okay, such that this, given a finite module, let's call the module M here, okay, such that M is isomorphic to, so going back to this color, M is isomorphic to, okay, Z mod P Z to the T1 direct sum Z mod P square Z to the T2 and so on up to Z mod P RZ to the TR. And moreover, and here is the so let me, moreover, M is uniquely determined meaning isomorphism always, as always, by these integers t1 through tn. Okay, so the module structure over such a ring is just like this. So determined by a tuple, R tuple of non-negative integers. Okay, now and therefore what we conclude from this is that, so this is a theorem, finer than the naive version that we saw in the beginning. And that is the following. So the primary decomposition theorem tells us that M is a direct sum of finite direct sums of modules over of this kind. And this theorem tells us that modules of this kind are, they are some prime power cyclic groups, a direct sum of prime power cyclic groups. So what you can conclude is that every finite abelian group is a finite direct sum of finite cyclic groups of prime power orders. So this is the extra thing that you get. Okay, so this is the new thing. So earlier we had only finite cyclic groups, but now you can even assume that they have prime power orders. Okay. Okay. Now all this is statements are good, but let's do some proofs as well. Let's prove the Chinese remainder theorem. But maybe there is one more thing I want to say before we get back, and that is from here we can even get the ultimate structure theorem that we are after is just one step from here. Okay, it's a bit of just present arithmetic, just keeping track of this, what these TIs are. Okay, so once we get here, we are almost done. So next time, what we will do, or even this time if we have time, is to understand how by putting the primary decomposition as well as this theorem together, we get the structure theorem for finite groups. The ultimate theorem that we want, which I have not stated before. We'll state and we'll also put model these two. Okay, and now what remains to prove is for the primary decomposition itself, we need to prove the Chinese remainder theorem. And then once that is done, we need to prove, we need to give a proof of this theorem. Okay. Now let's go ahead and tell you that this theorem is the proof of this theorem is analogous to proof of the existence of Jordan canonical form. Right. So there is a lot of similarity between that and this proof. Okay. So now let's prove the Chinese remainder theorem. Okay. Okay. So what we have, so proof of CRT. Right. Okay. Maybe we'll warm up by just proving this thing again, this statement that, so remember our assumption, A1 through AN are pairwise comaximal. That's our assumption. Okay. Then, okay, to show, let's show this. To show A1 intersect AN is actually the product. Okay, I want to show this. So let's do the proof. Okay, one proof could go this way. This is always true, always. No condition, you don't need pairwise maximum, co-maximal, nothing. This is just true for any ideals. So the content is actually here. Okay, and let's do an induction on N, and let's do the case N equals 2. Okay, so what we want is A1 intersect A2 is contained in, this is what we want to show, A1 times A2. Now we ask, of course, under the assumption that A1 and A2 are co-maximal. Okay, so what does A1 and A2 are co-maximal mean? 1 is equal to A1 direct sum A2. Right? Okay. Now suppose X belongs to A1 intersect A2. Right? So I think we did this last time, but let's anyway do it. XA1 plus XA2. So this is A1 intersect A2. And then notice on the right side, XA1, X belongs to A2. Therefore, this belongs to A1, A2. And since X belongs to A2, yeah, if I didn't say it correctly, I'm saying it correctly now. What is relevant is X belongs to A2. And once X belongs to A2, this product belongs to A1 times A2. And here, once X belongs to A1, this product belongs to A1, A2. Okay, so the right side belongs to A1, A2, and the left side was an arbitrary element of the intersection. So it's true. So the case N equals 2 is done. Now, for the higher cases, let us just observe the following. I think we did this last time, but let's do it again. So for the induction step, before we do the induction step, okay, for the induction step, so observe, okay, so let me even motivate that by looking at what we want. Okay. So you have, what do we want to prove? A1 intersect A2 intersect dot 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 intersect AN. This is what we want. A1, A2, AN. Okay. Now this by the induction hypothesis, this intersection is the product because this is one less number of ideals. So this will be by the induction hypothesis A2 AN by the induction hypothesis. So this is by induction hypothesis. Let me just write it as IH. Okay. And then now, if I can show that A1 and this product are co-maximal, then I can apply the N equals 2 case and get this. This is provided from N equals 2, provided N equals 2 case, provided A1 and A2 intersection AN are co-maximal. Okay, and let's see, can we prove that these are co-maximal? So what do we know? We know A1 is A1 and A2 are co-maximal, A1 and A3 are co-maximal, and so on. A1 and AN are co-maximal. So we can write 1 is equal to A1 plus A2. 1 is equal to, okay, maybe I'll write A1, 2. So A3 plus A3 and so on. 1 is equal to A1n plus AN, where this A12 belongs to A12, A13, etc., A1n all belong to A1, sorry. Okay, and A2, AJ belongs to aj for j bigger than or equal to 2. Okay, so we are choosing such elements. Now I can take just their product. If I take their product, so just 1 is equal to, the relevant thing to look at is a2 dot 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 a1n plus a. Now observe, so I'll not write this down, but I'll say it in words. Observe that here there is this a2 an. Now every other term has some one of these in it, but that belongs to A1. Any all of those belong to A1. So the only term that does not belong to A1 is this product term, but that belongs to A2 section A. Therefore, we have shown that 1 belongs to this sum, right? This belongs to A to AN. And so they are comaximal, and we are done with this. Okay. We had A, so let me change color. So we had A by A1 intersect AN. This, or rather, okay, let me write it the way, in the order in which I wrote. A2 AN, that product. This product is the same as this intersection. That we can write now, because that we already know because of what we observed, that the intersection is the same as the product. Now this, I want to say, is isomorphic to this. Okay, and actually maybe it's more precise to say that the natural map is an isomorphism. What is the natural map? Well, the natural map, so we have AI contains A1 intersection AN, obviously, for all I between 1 and n. Okay, so if an ideal contains another ideal, so this A1, for example, contains this intersection. So this is a smaller ideal, this is a bigger ideal. So there is a natural quotient map from the intersection to each of the quotients. Okay, and I'm taking the product of those. So this is the standard quotient. So call it this pi I if you want, right? And so what we are saying is that if I take the product, this map is given by the product pi 1 cross pi n to A mod A1 cross A mod AN. This is an isomorphism. Okay, right. Okay, let's see why this is an injection. Right. So you have a ring homomorphism. Think of it as, let's even think of it. You can even think of this as A going to A mod A1, A going to A mod AN, and then you have a map from A to the product, which is pi 1 plus pi. Right? And suppose something goes there, then that means its image A1 is 0, and its image in A mod A1 is 0, and so on until its image in A mod AN is 0, right? Which means it precisely belongs to A1 intersect AN. So the injection is rather obvious. Okay, let's do the surjection. This is where the content lies. So the idea here is that I must get some element here which is 1 and 0, 0, 0, 0. Suppose to show that it's a surjection, suppose I'll try to show that I can get an element 1, 0, 0, 0, right? And an element which maps to 0, 1, 0, 0, and so on, right? And if I manage to do that, so note that this is something I have to prove, because if I want to prove that this is down to the image. And once these belong to the image, then anything belongs to the image, because if I want, for example, something into this plus something into this plus something into this, I just take, so suppose I have B1 mapping to 1, 0, 0. Let me call this E, this is E1, this is E2, etc. etc. Okay, so B1 goes to E1. Suppose I have BK or BN goes to EN, right? Then if I want what goes to A1, AN, right? So suppose so you think of this as A1, E1 plus AN, BN, AN, EN, and you can just take A1, B1 plus dot, 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 plus AN, BN plus space. So it's rather easy to see that if these are in the image, then we are done with the surjection. And how do I get this? Now that follows because you have an element that is 1 modulo. Okay, so for example, how do I get, how, so what is B1, for example, right? We just saw that A1 and is comma A1 and A2, AN are comaximal, right? So I can write here A plus B, this belongs here, is 1, right? Observe that this B belongs to this product, therefore their intersection. So this B is 0 modulo AJ for all J bigger than 2. On the other hand, this belongs to A1. So B mod A1 is 1. So this is my B1. So this indeed, I can this to be, choose this to be B1. And how do I get B2? This A2 and A1 intersection A maximum for this, for the same reason that these two are, and so on. Okay, and so this proves the this completes the proof. So let me just write it Q. And to prove the Chinese remainder theorem. So let me just do a quick recap. So you have this theorem, you apply to the ring Z mod DZ, where D you have chosen such that you have given an abelian group, and then you choose this D such that D times M is 0. Right? And once you've done that, you have this decomposition of D by the fundamental theorem of arithmetic, P to the R1, Pk to the Rk, and then you use this and apply the Chinese theorem to say that this ring is the product of Z mod P1 to the R1 cross dot 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 cross Z mod Pk to the Rkz. And from there we get the primary decomposition of M.
I shall begin by just recalling what we did last time very briefly before I continue. Maybe this is a good time to ask if you have any questions. Very quickly I can answer your doubts if you have any before I proceed further. We have this map from, so call this X, sometimes E power something, So n by n matrices over real numbers to GL n R, and the same thing exponential mn n cross n matrices with complex numbers entries to GL n C. Okay, defined as okay, so x goes to summation, so x power k by k factorial, k going from 0 to infinity, and this is what we call exponential of x. Sometimes we write it as e power x also. Okay, and we saw that when you vary x in mn of R or mn of C, this is first of all absolutely convergent and uniformly convergent on bounded subsets of the domains. Okay, and it's understood that the norm that we are using here is a sup norm, and here also the same. Okay, so this is and we saw some important properties of this, namely d by dt of e power t times a for any a, or a in the domain. Let me write m and c here. T varies in real numbers though. I mean, you can also allow t to vary in complex numbers, and then it's complex differentiation. But anyway, we saw that this is same thing as a e power tx. Yeah, and some of the, I'm not going to recall all the properties, but some basic properties I shall recall. E power p x p inverse is same thing as p e power x p inverse is one thing we saw. And yeah, another important property, if a and b commute, ab equals ba, then the usual thing holds, property e power a times e power b is equal to e power a plus b. Okay, so this is an important property, and we saw several other properties and some examples. I will recall as and when required if a particular property is used. Okay, so for today I shall begin with one calculation. The previous time we did several calculations, but this time I want to do a simple enough calculation, all right, but it's not going to be just a upper triangular matrix or something. So let us just take very simple, but I have just to save time because calculations take a long time. I did this just before the lecture. So I take this matrix 1, yeah. So this is example. Okay, so compute e power a, and now you know, so this is not going to be that easy because yeah, so what is a, okay, one formal way of doing things is, you know, a certain equation that a satisfies, namely its characteristic polynomial. So a satisfies this equation, a square minus trace, so 4 times a, and then plus determinant, this is 4 plus 3, I suppose, yeah, this is equal to 0. Okay, so you can write a square is equal to, therefore a square is equal to what, 4a minus 3 and repeatedly. Then you can write a cube equal to something 4a square minus 3a, and then you substitute for a square and so on, and then you substitute all these things in here. Finally, you still have to calculate. You will get some linear expression ultimately. In here, you will just have only two terms, constant term and a term involving a, but with some coefficients, of course. And it's a non-trivial task then to compute those coefficients. Yeah, so it's a bit unwieldy to proceed like this. So instead, what we are going to do is use some properties of the exponentials that have been already established to compute e power a. All right. So notice that I have actually I just deliberately took it to be a symmetric matrix. I did not have, nevertheless, I have a symmetric matrix. Anyway, you have written down the characteristic polynomial or equation that is satisfied by a, and this factorizes very nicely. So a square minus 4a plus 3 factorizes factorizes as what? A minus 3 times a minus 1. Okay. Yeah, so just if you like, you can write lambda here, but anyway, I'm going to write here. This means that the eigenvalues of, therefore, the eigenvalues of A are 3 and 1. 3 and 1. Okay. So, eigenvalues being distinct, matrix A is diagonalizable. Okay, and in fact you can find out the eigenvectors. So I did that calculation. Otherwise you all know how to do that anyway, right? So a, so we solve for, solve a x is equal to 3 times x, and parallelly a y is equal to 1 times y, which is y. And now you take this a minus 3. Okay, so you know how to solve this, and it turns out that I solved this anyway. So take x to be equal to 1, 1, and here y is equal to I think 1 minus 1, but we will verify these things. Okay, very quickly. What is 2, 1, 2, 1, 1, 2? Evaluate, multiplied by 1, 1 gives me, well, 2 plus 1, that is 3. 1 plus 2, that's also 3. So that's exactly correct. So now, likewise here, you can compute a times 1 minus 1, that's equal to 2, 1, 1, 2, 1 minus 1, and that is 2 minus 1, which is 1, and 1 minus 2. So when you do this, 1 minus 2, which is minus 1. So therefore, these are indeed the eigenvectors. Okay. And now take P is equal to, so therefore, take your matrix P to be the one formed by eigenvectors of A, which is 1, 1, 1, minus 1. And then you have to compute P inverse. So therefore P inverse is equal to, you can do the calculation of P inverse. In fact, its determinant is minus 2. So I will have to divide by minus 2. Okay. So after you simplify, you get this 1, 1, 1, minus 1, which is again 1/2 of P. Okay. Yeah. And then what do? You notice this calculation. So PAP inverse, this better be a diagonal matrix, and in fact we compute what it is. This is 1/2. This is just matrix calculation, and you should get a diagonal matrix. Yeah. So 1 1 1 minus 1, and then 2 1 1 2, and it's convenient that P inverse also is a multiple of P, so it's very easy therefore to do this calculation. This gives us what? This is equal to, okay, so should I do this? I don't know. So 1 by 2, 1 1 1 minus 1, and here this is, yeah, this matrix times the first vector, that is 3, and this matrix times the second vector, which turns out to be the same, 1 minus 1. And now you really have to make this calculation. So this turns out to be 1 by 2. Now 1 1 here, 3 3, that becomes 6. 1 1 minus 1, this is 0. It should be expected. This 1 minus 1, 3 3, so that is 0. 1 minus 1, 1 minus 1, that becomes 2. So 1/2 of that is the matrix 3 1. Of course we know this, okay, because we formed our matrix P using the eigenvectors, and it's no wonder therefore that you get this calculation to be the diagonal matrix whose diagonal entries are the eigenvalues. Notice this 3 1, they are exactly the eigenvalues. So this should not surprise you at all. We all know it. Okay, and now you see you can compute exponential. So e power PAP inverse, this is easy to compute, is e power 3 1 along the diagonal matrix is, this is diagonal matrix e cube, diagonal matrix e power 1, which is just e. Okay, but on the other hand, this is equal to, okay, let me write this, P e power a P inverse, right? So let me write here, therefore this is equal to e cube e. So what is e power a? Therefore e power a is equal to P inverse e cube e diagonal entries and P. And this is a simple enough calculation. And if I have done this correctly, I get something like this. This you can check at home. So I write here, just 1 second. I want to minimize this. Okay, gone. Okay, so I write it in green, but you please verify at home. This is easy calculation, but no guarantees. I have not made a mistake. So e square by 2 and e cube minus e divided by 2, and then e cube. Yes, it should be symmetric matrix minus e divided by 2, and then e cube plus e. This is surprising to me that this is what I get. Okay. All right. So this is what I get. You just please check this whether what I have done is correct. It's a simple matrix calculation, so it should be easy. Okay. So sorry. I seem to have not e square here. E. Erase that square here. This is what I seem to be getting. Anyway, check. What is a comment I wanted to make about this calculation? Yeah. Okay, so I took a sort of a convenient matrix which has real entries and therefore it was diagonalizable. it's quite possible that you have a more complicated matrix, and then yeah, so the problem is it may not have real eigenvalues. Then it will not be diagonalizable. But then you go to the work with the complex numbers. There you will be able to upper triangularize it. And once it is upper triangularized, it's really very easy. Okay, why so? Because the diagonal entries, you know. So let me say that. Yeah. I probably did one example last time, so I'm not going to do an elaborate example, but maybe make a few comments. Yeah. So suppose that yeah, so yeah, so I so okay, you can not only conjugate it to an upper triangular matrix, but you can put it in its Jordan canonical form, working over the complex numbers. Okay, and then block by block, it will look like, yeah. So this remark that I'm making will be useful in general calculation. So suppose that A is of the form some okay, lambda I plus some B, where B is strictly upper triangular. And what does that mean? That is, B is equal to, it's of this form. So diagonal entries are all 0. Down below, everything is 0. Here, there may be some stuff. That's it. This is strictly upper triangular. Okay. Now, the nice thing about B is that B is an nilpotent matrix. Then B power n equals 0, where n is the size of this matrix. Okay. I'm not changing that notation. Also, notice that identity matrix commutes with B, therefore lambda I also commutes with B. Lambda I times B is equal to B times lambda I. Therefore, okay, therefore, what can you say about the exponential of A? This is equal to e power lambda I plus B, but these two matrices commute, therefore this becomes e power lambda I times e power B. And why is it that this is easy? This is because, well, you just say lambda I is now even a scalar matrix. So it will be e power lambda, e power lambda. And here it is 0, here it is 0. Times, what about this? Why is this easy? This is because, well, you write down the definition. Here it becomes one identity plus b square by 2 factorial and so on. You need only go up to b power n minus 1 by n minus 1 factorial. That's it. No need to go any further because b power n is already 0. Yes. So this, in principle, at least you can compute this polynomial because you know everything about b. You see, when you take powers of b, the number of zeros keep increasing. The non-zero things get shifted in the sort of, so to say, northeast direction. So, okay, so now you can compute this. This is now, yeah. So, this is a scalar matrix. Whatever it is, you just multiply each row by e power lambda, and that will give you e power a. But you know, a general matrix X, whether it has real entries, complex entries, etc., can be put in block diagonal form where each block is like this. Okay, so sorry, first of all, I should say in the Jordan canonical form where the non-trivial blocks, diagonal blocks are of this type. and you know how to compute for these, and distinct Jordan blocks they commute and so on, and it's a simple matter therefore to compute exponential of A. So I have sort of I hope I have convinced you that in principle you can do the calculation, reduce the calculation to some simple polynomial type calculation after you have found put your matrix in upper triangular form, which you can always do over complex numbers. Over real numbers you may not be able to do, but over complex numbers you can always do it. Okay, so now let's proceed further. Yeah, so now I'm going to talk about some property of the exponential map, which is extremely important. So we have a map, yeah. So exponential from, you can work with real numbers or complex numbers. Let's just work over real numbers. I'm going into GLNR. Okay, and this is this exponential map. Okay. Now we already know that it is continuous, and you know it has its power series expansion and so on. Now we want to say that this is, so the statement is that the map expert is what is called a local diffeomorphism. Diffeomorphism around the origin. Zero matrix in Mn of R. Okay, let's just do that. I should explain to you what it means to say local diffeomorphism. So what this means is that if you take so that is there exists open sets U containing origin in Mn of in n by n matrices, and V actually in contained in GLNR. In fact, the image has to map into GLN. So GLNR has two components, those with positive determinant and those with negative determinant. And this goes to stuff with positive determinant. And that's because we already saw that determinant of an exponential is exponential of the trace of A. So exponential of anything is positive. So therefore it goes into GLNR plus, but let's not worry about that. And this contains the identity matrix, which is actually the image of V power 0. Image of V power 0 is the identity matrix, and V is an open set. V open. Okay, such that so again just let me write x goes to e power x, define is, so think of this as a map from such that, so you have a map u to v defined as follows. So this is the exponential map, restricted to u, and the codomain is also restricted to v, is 1 to 1 on to, and has an inverse which is also smooth. Of course, exponential is always already smooth, so we know that. But this is also, inverse is also smooth. Okay, and in fact, so you see, in fact, we can choose so the inverse. I make the statement and then I'll explain. In fact, the inverse map from where to where? V to u, okay, is denoted, sorry, is denoted most appropriately a log, yeah. So log, okay, b to u. And how is this defined? I'll write that definition, but maybe not elaborate on it too much. Log of, well, any element in here is in the neighborhood of identity map, so I may as well write it as I plus x. Okay, and this is equal to x minus x squared by 2 plus x cube by 3 and so on, minus and so on. Okay, and of course you need to worry about convergence and so on, but if your v is appropriately chosen, then this becomes convergent. Okay, so yeah, so the inverse is called the logarithm. So log of 1 plus x, identity element I plus x has this expression, but forget about actually getting an exact expression for this. A name should of course be log. It should be called log because the other one was called exponential. How do you know that this is in a neighborhood? It is 1 to 1 on 2 and has a smooth inverse. So that is a consequence of some statement. I mean, this implicit function theorem in real analysis. So I will just explain that. So here, yeah. So in fact, I for the so this is the comment for the proof. For the proof, we need only show that the Jacobian matrix of the exponential map x at identity at 0 is invertible, is non-singular or invertible. Okay, equivalently. So let's okay, so you understand, see, when you have a smooth map, how am I doing in terms of time? Okay, I should not elaborate too much on this. So I write, you understand, you have open map of open set of Rn square to another open set of Rn square. You have a smooth map. So you can just write the, it makes sense to talk about the Jacobian matrix. And you can evaluate it at origin. Okay, so it makes sense. Once you evaluate it at origin, it will be a matrix with the real entries. Okay, and now matrix with real entries, you just need to only say the determinant is not equal to 0, and that's exactly what this will guarantee, that the map in a small neighborhood, it may not be on the whole thing, but in a small neighborhood, it is 1 1 onto its image, and the inverse is also smooth. Okay, so that is the thing, but I'm going to say it in a slightly different way, which is the same thing, which is packaged in this particular way. So if you recall, so you have an open set in Rn, or you have actually Rn square, yeah. So I look at the what is called tangent space to Rn square, which is for us Mn of R, like it's a Euclidean space anyway. Consider the tangent space to this at this, and this is again of course isomorphic to or equal to canonically just Mn of R. Okay, so okay, the coordinates here, matrix coefficients, so if you are written as xij, d, it will be the basis for this one will be dxij evaluated at the origin. So here, so this you just consider it as the Eij, so to say, the elementary matrix Eij, thought of as an element in here. You know, Eij means ijth entry alone is 1, rest of them are 0. That's it. So you can just identify this. This is what we do when you have a smooth curve. You can talk about the tangent to a smooth curve. I should draw a picture. I think maybe that will help. So, but let me complete this and then draw a picture. This goes to tangent space at identity of GLN R. This is not quite a vector space, but it's an open subset of vector space, and this can again be identified with Mn of R. Mn of R. Okay, again, same dimensional. Yeah. Now, this map, what is this map? This is d by dt. Well, so I will write here not d by dt, but I will write here differential of the exponential d of x. D x. This is the way to write it. Okay, and now I will draw a picture here. Okay, yeah, so here I have origin. You can think of this as u or mn of r, it doesn't matter. This is just a schematic picture, and this is my gln or. Okay, now this under exponentiation goes to the element identity. Now I have a tangent space here which I just draw like this, and I draw a tangent space here like this. Okay, and now I'm going to take a different color. So I take a tangent vector here like this. This goes to some tangent vector. What is that vector? Let us see. So here, so a tangent vector here is just a matrix A. Okay, so this is just matrix A, and we know that A is actually realized as a tangent vector of the curve. So TA, right? So I have a smooth curve. If you like, you can write -1 to 1. It doesn't really matter to this space in here U, which is just T goes to TA. And now apply exponential. Then I will get the curve. The composition will be, of course, this will be taking values in the GLN, and there. So this is like just a straight line curve. Here it's going to be a curved thing like that. Okay, so maybe I should have drawn. So and t will go to e power ta. Okay, and what is that d by dt? This d of exponential, d of exponential. What does it do to a tangent vector at origin? Tangent vector a. This becomes equal to d by dt at t equals 0 of this e power ta. And we know how to compute d by dt of e power ta. That's equal to a e power ta evaluated at t equals 0. And when you evaluate it at t equals 0, you actually get a. So in fact, you get the same vector. A goes to a. But that's an isomorphism. Yes. So that's an isomorphism of vector spaces. This is an isomorphism of vector spaces. Is the same thing as saying that the Jacobian matrix is invertible. In fact, if you write the Jacobian, that is just the matrix of this with respect to these bases, the coordinate vector fields. So all told, so to summarize, what this whole calculation that I have written down shows is that d of exponential at origin is an isomorphism. isomorphism of real vector spaces. So I put real in bracket vector spaces. This implies that this implies Jacobian is, well, this is equivalent to actually Jacobian of x is not equal to 0, and that's all we need to show. So this implies exponential is a local diffeomorphism. And let me just comment that one remark. So remark, it is not a global diffeomorphism. It is, so it meaning, sorry, I should be careful. Exp is not 1, 1. You may wonder whether Exp is globally 1, 1. Exp is not 1, 1 globally. And the easiest way to show this, you can even look at one-dimensional case. Well, one-dimensional case sufficiently, I mean, suitably modified, but I will essentially do the one-dimensional case. So you see, you take this 0, 0, 2 pi. Yesterday we did this calculation, right? So t minus t here rather. So exponential of this, we calculated it. What was this? I suppose it was cos t sin t minus sin t cos t, right? Now put t equals 2 pi, then exponential maps it to, yeah, so 0, 2 pi, 0, 2 pi minus 2 pi 0 is also equal to exponential of 0 is also equal to identity, which is exponential 0. Yeah, so typically it is not 1, 1. You should not expect it to be 1. All right. Yeah. So next thing I want to talk about, maybe for a change. See, I have a few things in mind to do. Let me just give me 10 seconds. I will decide what I want to talk about next. One of the properties I mentioned was the following: e power a transpose is equal to e power a transpose. This is more or less obvious. There is nothing to it. Okay. What I want to do is, let me tell you what I want to do. We want to analyze the exponential map in the following situation. When so when here again I will say it in the following way: when it is restricted to the following vector spaces of A, Mn of C, Mn of C, Mn of R, okay, depending on the context. I may discuss only one of them and not discuss the other, so for want of time, okay. So what are the subspaces? I will write here, so space of all skew symmetric matrices. So let me be a bit vague about it and simply write it as SKN. SK for skew. Okay, I'm not mentioning the Well, okay, if you want, you can do this. Skn of R. And yeah, so what are the other spaces where I want to restrict? Sorry, I don't have too much board space. So symmetric, but symmetric matrices. But before that, maybe space of skew Hermitian matrices. Hermitian matrices, which I may call them, I don't know what to call them. SH, skew Hermitian matrices. This is necessarily contained in Mn of R. Okay. And then subsequently, so symmetric space of symmetric matrices and Hermitian matrices. So let me write all these and let's see what we get out of these things. Okay. All right. So let us take first one. So maybe I should label them 1, 2, and 3. And 3 contains 2 parts. Let's see. So let us take 1. So what is a skew symmetric matrix? Skew symmetric, so recall. So X is skew symmetric if X transpose is, sorry about the bad handwriting. Just wrote something, may as well write this properly. X transpose is minus X, yeah? X transpose equal to minus X. And so is it clear that it forms a vector space? So it forms Skn or is contained in Mn of R is a vector subspace. Is a vector subspace. Because you see, if you take A plus B transpose, that same thing as A transpose B transpose, and from that it follows this is actually a subspace. All right. Now note that X transpose, okay, and X commute if X is skew symmetric. This is a trivial statement here. Skew symmetric. Okay. Now, yeah. So let us therefore we know that, well, identity matrix. Okay. Let me write like this: e power x whole transpose times e power x. This is equal to e power x transpose times e power x. But x transpose and x commute. So this becomes e power x transpose plus x, since x and x transpose commute. Not always true. So this is where it's crucial that you are working with skew symmetric matrices. This is equal to, what is that? Yeah, so x transpose plus x is 0 and e power 0 is identity. What does that mean? This means that, so this implies that e power x satisfies the equation. If you write this is equal to a, set this is equal to a, then A transpose A equals identity. That is E power. So that is A is orthogonal. A is orthogonal. And in fact, and we obtain so from the exponential map, yeah. So exponential map maps skew symmetric matrices for real numbers to orthogonal group ON. And if you work with C, it's the same. There's no difference, except that in the case of real, like I already said, this is exponential takes values only in space of positive determinant matrices, but orthogonal group will have matrices with negative determinant also. So this will not be onto in that case. But in the case of actually orthogonal group over complex numbers, you don't need, this is not an issue. Let's not worry about that too much. Okay. So what we have proved is that on the, so notice that we have already shown by what I had said earlier that it is okay. There's a slight. Let me make this following statement. This is the image. Okay, the image. I have some 20 minutes. The image is precisely SON, which is space of all matrices A in Mn of R. It's called special orthogonal group such that A transpose is identity and determinant of A equals +1. The image is contained in here. That's obvious from this calculation. It's actually equal to, and how to show it is equal to, well, okay, so yeah, if A is, let's assume that A is special orthogonal, then you can conjugate A to a matrix which looks like 2 by 2 blocks, and the last entry is 1 or -1. It's in fact equal to 1 when the determinant is actually 1, where each 2 by 2 block will look like cos t sin t minus sin t cos t and so on. Let me short circuit that statement by saying the following thing. Yeah. So if I just take, maybe instead of this orthogonal matrix, I just take this. If X is equal to, okay, these type of 2 by 2 blocks, T1, T minus T1, and of course 0 here, and this type of blocks you take, okay, 2 by 2 blocks, and you have to go all the way, and finally here another 2 by 2 block, 0. I think this is becoming too detailed, but I started to say this. And depending on whether n is equal to 2m or 2m plus 1, depending on that, you can put a 1 here. And you look at the image of this. Other unspecified things are all 0. Okay. So then you can just check that if this is the case, then exponential of x becomes like 2 by 2 block. So I will write here r theta 1, rt1, so block diagonal, okay, rtn, okay, and maybe there is a 1 here depending on the lost the parity of n. So one may or may not be present. That depends on the parity. Where RT is the rotation matrix, RT is equal to cos t sin t. Sin t minus sin t cos t. And then it's a huge general fact that if you take any, so these elements are all there, okay? These elements, such elements are all there in the image. Now an arbitrary SON matrix is actually conjugate by again an orthogonal matrix to, in fact you can make it special orthogonal, to a matrix of this type. And that proves that actually it is onto. So I noticed. Yeah. So that shows that this is precisely, image is precisely this. So this, okay, I went a little too fast and probably, yeah, the main thing is that once you know that this is what is called maximal torus, this is like S1. The image is this an element of S1. This is actually an element of S1 cross S1 cross S1. So n-fold copies. So this is called maximal torus and so on. Now the main point is that when you look at an arbitrary element, that may itself not look like block diagonal forms like we have here, rotation matrices, but it is conjugate, in fact, by an element of SON, so that it becomes block diagonal in this particular fashion. So that allows you to show that in fact the exponential map is surjective. And now once you know it is surjective, even so some additional work is required, but so on the other hand, you can actually compute what is the dimension of the spaces involved. Probably, okay, I don't want to talk too much about it because then I will be talking about manifold theory and so on. Let's leave this discussion at this stage. I want to say that this inverse image of ON under the exponential map is precisely the skew symmetric matrices. Okay, and in particular, so you can say that the tangent space, just like we had tangent space to the GLN, at the identity was the full Mn of R, you can say the tangent space to On at identity is exactly the skew symmetric matrices. Okay. And I don't want to talk too much about this Hermitian. I think I listed that somewhere. Skew Hermitian. Was it number 2? Yes. I'll be brief about that. What is the statement? So skew Hermitian, X is in I wrote SHN, skew Hermitian. Recall the definition, if and only if X bar transpose is equal to minus X. Okay, now you see this is sub of complex matrices, Mn of C. Okay, so X bar transpose makes sense. Of course, if X is already having real entries, that same thing I reduces to just X being skew symmetric. Okay, and again you can show that in this case, in fact, skew Hermitian is much easier to deal with. In this case, exponential of X is a unitary matrix. Okay, so that is, so if I call this is equal to A, that is A satisfies A bar transpose times A is equal to identity. The proof is almost the same as for how we showed exponential of a skew symmetric matrix is orthogonal. The only added thing is you have a bar here, complex conjugation. And like I pointed out last time, exponentiation commutes with the conjugation. Exponential of x bar is same as bar of the exponential. So that fact also is involved in the proof of this. That's all. Otherwise, the proof is identical, and I don't want to expand on that. But I want to recall for you what is this unitary group. So UN is actually the space of all matrices A such that A bar transpose times A is actually identity. Okay, and this is, yeah, I should have emphasized that last time also. This is a group. It's a just like here also it's a group. They are precisely this, which is a group. So I should emphasize it, which is a group. I should have done this. So you see, you took certain subspaces, the image turned out to be a group. So here let me again emphasize that this is a group, okay? Everybody knows unitary space of unitary matrices forms a group, okay? You can just directly verify that. It's a very simple verification. I don't want to do that. Yeah, so let me talk about one other thing. This one I already commented about. I have listed number 3, symmetric matrices, Hermitian matrices. Let me talk about it a little later. But before this, I want to emphasize another example where we had a group as the image. So take well, the standard notation. Okay, let me just forget about standard notation. I will write here 0. This is equal to space of all matrices such that trace of A equals 0. And again, this is a subspace. This is a vector subspace of Mn of R, vector subspace. Okay. And what is its dimension? You can compute it. It's just defined by one linear equation. Dimension of M0 and R is actually equal to n square minus 1. All right. Now we already saw that exponential maps M0 and R to which space? SLNR. And what is SLNR? This is what is called special linear group. Like GLN, general linear group, this is special linear group. Space of all matrices A, such, well, determinant of A equals 1. And here I could work with also complex numbers, definition is the same, and so on. Okay, now just I'll make 2 statements and stop. What is so special? So you may, first of all, you can ask a question. This question should have occurred to you by now. If V is a vector subspace of Mn of R, is a vector subspace, is it true that is it true that image of V, so exponential maps V onto a group, onto a subgroup of GLN, or likewise for C? So this is a question. We should it looks like in the examples that we saw so far, it seems to be the case. And I'll just tell you answer. Not true in general. Not true in general. So therefore the question arises, when is it true? So the thing is, it is true. Here also there is a Well, some subtlety here, I just ignore that subtlety for the time being. Maybe I will say just a few words about it in the next lecture. It is true if V has the following property, has the following property. What is that property? If X, Y in V implies that this what is called bracket or Lie bracket xy, which is defined as xy minus yx. You see, this is matrices. These are matrices, so I can form this commutator xy minus yx. This must also be in V. Okay, so for all xy, yeah. So this for all I can put here. Erase this. Put that here. For all xy in V, this is also called Lie bracket. Lie bracket of xy must be in V. Okay, if this happens, then it is true. In particular, if V is one-dimensional, this is always true because everything is a multiple of a single A. So xy minus yx is 0. One-dimensional, this is true. And you can go home. So that's my next exercise for today. So I will write that. Okay, exercise. Show that, yeah, anything which satisfies this property has a name. It's called V, is then called a Lie algebra under matrix multiplication. Notice, we are not saying that xy by itself must be in V. We are not at all saying that. That's not even true. What is to be expected is that xy minus yx is in V. Okay, so I will say that, so this property I will give it a name. All right, I should stop pretty soon. This property, so if star holds, we say that V is a Lie algebra. V is a Lie algebra. Yeah. So I'm going to give one exercise for you to try. It's a very nice exercise. We show that I already introduced this notation Qn or actually also Qn of C and then M0n of R, M0n of C or Lie algebras. This name Lie refers to a mathematician sophistly. And I stop here and let me stop sharing. How do I stop sharing? How should I? Yes, okay. I think I can say stop sharing. No, stop sharing. Yeah, this window. Okay. So if there are any questions, you can ask me.
Sir,
Do you have any questions? Yes.
There are some questions on the chat box, sir.
Oh, okay. So why tangent space of GLN is isomorphic to this? Very nice question. What is a tangent? That's a good question. I will answer that. So I should share again, I suppose. Just 1 second. Yeah. So let me share my screen. I'm going to answer your question using diagrams. Good question. So, okay. So you see, what is a tangent? What is a tangent space? So this, remember, this is my picture of GLN. Pretty bad picture, I agree. And of course, it's contained in some Euclidean space, Mn of R. Okay, it's an open subspace. So what do we mean by tangent space? to GLN at a point. So one has to understand what is the notion of a tangent space to answer that question. So tangent space consists of all tangent vectors. What is a tangent vector? Tangent vector is a velocity vector to a smooth curve which lies entirely in GLNR. Okay, so I draw a smooth curve and then take derivative at time t equals 0 when the curve passes through that point at time t equals 0. Okay, but if it is an open set, not necessarily GLN, any open set, I can take a straight line segment. You give me, okay, so in here, so here I just in Mn of sorry, it's supposed to pass through origin. It's difficult to draw with this medium. I am not good at this. So I have to draw, I have to give myself a tangent vector, right? So that means why is it that tangent? So this, I give myself a vector here in Mn of R. Okay, call this A. This is my vector. And now I must give a smooth curve in GLNR passing through identity and having velocity vector at time t equals 0 to be equal to A. So you just do the following thing. Mind you, A is okay. So you just look at this. The curve will go from -1, 1 to GLN of R. Just map T. So T going to identity matrix plus T times A. Okay, where A is the vector in Mn of R. That's just a matrix, n by n matrix, but you just think of it as a vector. Now, this may not be invertible for all values of t. In fact, it may not be invertible for points -1 to in this interval. But if t is very small, so I change my domain. If t is some epsilon, so t varies in -epsilon, epsilon sufficiently small, having fixed your a, this takes values in GLN. Or for all t such that mod t is less than epsilon. You can always show this. Given a is always such a thing. Now you take derivative d by dt of this curve. So sigma of t. What is it? D by dt of, so I is constant matrix I plus d by dt of t times a. Okay, now this constant matrix has derivative 0, so this is 0. And now this d by dt t times a is just a. Okay, so every matrix arises as tangent vector. So the collection of all tangent vectors here, therefore, is Mn of R. That's it. There is nothing more to say. That's all. That's a proof that the identity, the tangent space at identity at to GLN R is exactly the vector space Mn of R. Any further question?
There are still more questions in the chat box, sir. First one, why is it that an exponential of a matrix always invertible?
So yes, I'll explain that. We did that last time. So yeah, so A commutes with. So you want to say that this is invertible, you just take times minus A. But A and minus A commute. See, this is equal to A plus minus A. This is equal to e power 0, which is equal to identity. This is 0. Okay. Now here is where you have to say, since A commutes with minus A. In general, e power A times e power B is not e power A plus B. So you have to be careful each time you use such a property, ensure that A and B are, but here A and minus A. So you see that what does that mean? This is invertible, this is also invertible, this is the inverse of this. Okay? Any more question, please?
Then it is smooth in which sense?
Which one is smooth in which sense? Oh, the curve I wrote.
The question, yeah.
Okay. So you see, I think I wrote this curve. T goes to, I don't know, in the answer to my previous question in the chat box or in the general. So I don't know which question. So this is one thing. This curve, is this what you are asking, whether it is smooth? We computed the derivative of this. D by dt of this. See, if you can compute the derivative, then it's differentiable once. You can keep on applying that repeatedly. You get, it's a smooth curve. So you see, once you apply this, e power ta, briefly let me write this like this. This is equal to a e power ta. We showed this. You can again take second derivative, third derivative, and so on and so forth. So you say some curve is smooth if it is differentiable any number of times. Okay. If you were talking about the other curve, that's also smooth. T goes to T plus, sorry, identity matrix plus T times A. Well, this is just a linear curve. You know, as a curve, as T varies, what do you pick up? You pick up a straight line, yeah, passing through identity matrix and the matrix A. When you put T equals 0, you get identity matrix. When you put T equals A, you get A. Sorry, when you put T equals 1, you get I plus A. Sorry about that. But the whole straight line may not be in GLN, but when T is very small, a small line segment is contained in GLNR. This much part of the straight line is in GLNR. This is what I was saying, if that was the concern there. Because you have an open set, yeah. What do you mean by open set? Given any point here, namely identity here, there's a small disk, open disk or open ball around it, which is entirely contained in here. I take my T to be less than the radius.
When we consider it as a subset of r to the power of n into n, differential with respect to each coordinate.
Yes. So the coordinate functions are all written like this. See, let us do it for 4x4 matrix. So in a 4x4 matrix, you will write like this: xij, I varying from 1 and 2. So this is identified with. You can write it in any order. The order doesn't matter. So the most natural one is you just list the column vectors. You know, if you are doing some calculation in a computer, this is how you will feed. The numbers. So this is 2, not 3. Okay. So 4x4. This will be in R4. So give me a vector in R4. I will make a matrix 2x2 matrix. This will be in GL2 or M2 of R. So this is how we have been regarding Mn of R. So if it is 3x3, you will get a vector consisting of 9 components in R power 9. Instead of writing x1, x2, x3, x4, you write x11, x12, x21, x22. That's all. But it really doesn't matter. If you are bothered by it, you give it some other label: y1, y2, y3, y4. It doesn't matter what you call those coordinates. Any further question?
Sir, there is an answer from that person you have explained, right?
Okay, yeah.
Sir, you have computed derivation of exponential at 0 is basically the identity map. How to compute derivative of exponential at any matrix of A?
That's, yeah. You can always compute it. That's not a problem. Exactly follow. See, once you know the definition of that map, see, it's just like, okay, let me explain that in general terms. So f is from some open, from Mn of R, which is r power n square, to some open subset in this one, but let us just write it again as a matrix. So this is how I, very first line of my thing had Mn of R. So then f will have coordinates. So f of x will be f11 x blah 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 fnn x. Okay, I'm using, and now each one is smooth, and you can just take derivative at any point. So yeah, you have to compute. This is what I was talking about, the Jacobian. So you compute. So the Jacobian of f, okay, is equal to d f I j of x with respect to d. Let us write here x k l. Okay, so this will be an n square by n square matrix. N square by n square matrix. This is how it is computed. Yeah, if you stick in some other matrix, not necessarily origin, okay, so this is Jacobian. So some other matrix A, you have to evaluate it at A. Okay, so that's all you have to do at A. After you compute this, you substitute the values of A. You see, you will get some expression which involves x, that x is xij, and wherever you have xij, so you substitute. So let me write A is equal to aij. After you calculate this will be a bunch of functions. You see, after you compute this, you substitute the values of xij to be aij. That's how you compute it. I think I should stop here.
So last time we defined what is a group action. Let me just recall. Let G be a group. And G is said to act on X if there is a map from G cross X to X such that the group element take G and element in the set X so G times on X. So G cross X to X, G comma X, the pair maps to G times X. So that means G is the group element takes element X in X to some other element which we denoted by G dot X, satisfying the following. One, the group identity element of the group will take everything to itself. That means E times X is X for all X in X. Two, G1 acted upon G2 dot X is same thing as you look at the multiplication G1, G2 in the group and take that element, multiply G1, G2 and acts on X. Okay? So if these two properties are satisfied, we say that the group G acts on S. Okay? On the set X. Okay? So we have already seen several examples. Say, for example, let X is 1, 2, etc. N, where N is a positive integer. And I showed that set of bijection of any set is a group. So this Bx, the set of bijections of X, F is a bijection. Is a group under composition of maps. Bijection is a map from X to X. So this composition of map and is denoted by this group is denoted by Sn, where n is that number. Okay. So note that you have such a example, and the Sn acts on set 1 to n to 1 to n. So if sigma is a bijection from 1 to n to itself, and if you have any element k in this set, it will take to the value of k under the map sigma k. So this is by definition is equal to the definition of sigma dot k, means in this case. Okay. So this is one such action. Okay. So now, before going further, I would like to introduce two notions. One is so this I will go back to the general thing. Let G acts X, then the set, then set G. So let me just and X is an element of X. Okay. Then we define a subgroup. So then consider Gx equal to set of all G in G such that G times X equal to X. So this is called the Gx is a subgroup, easy to verify, of G, and is called the stabilizer of X in G under the action of G on X. Okay, this is one thing. Two, I will also define a subset of X. So say let G and X, G acts on X. X belongs to X. I define a subset. Then X is equal to set upon G times X. G belongs to G. So this is a subset of X. OX is the image of the element X in X with respect to the various elements of G in G. Look at that subset. So this is called the OX is called the is known as the orbit X under the action of G orbit of X under the action G on x. Okay. Let's look at examples. Look at x equal to 1 to n and g equal to Sn. Okay. So then if I take x to be equal to n, okay, so then what is gx is set of all sigma belongs to Sn, that sigma of n equal to n. That's what it means. Okay. So this is a subgroup which we can identify with Sn minus 1, because if you take any permutation of 1 to n minus 1, then we can extend it to a permutation of 1 to n by sending n to n. So this I can identify with Sn minus 1. Okay. Yeah. So that means it's a permutation of this subset 1 to n minus 1. I can identify with that permutations of that, or the bijections of that set. Yes, this one. And so in this case, if I take 2, what is O of x is as above, x and x equal to 1 to etc. n, g equal to Sn, and x is again n. Then what is O of x? So this you will see that is equal to the whole of x. Okay, so in general, this may not happen. So let me just on that say something definition. Let G be a group acting on a set X if for some X. So if you show it for one X, it will also follow for every X. If for some X in X, OX is whole of X, then we say that the group G acts transitively on X. Okay. So this is the example that I gave is one such example. Okay. For example, in general, it need not happen that the action not necessarily transitive. For example, let's look at some example. Let x equal to 1, 2 cross 1, 2 and g equal to S2, that is the set of bijections P of 1, 2. Okay. So then I will define an action on S2 on X. Namely, take an element sigma here and take a AP in X. So then I want to define again an element of this thing. So how do I define? So this I send it to sigma of A, sigma of B. Okay. So I have defined this action. Okay. So let's look at this action. What are the orbits? So claim is that now this action is not prime. So this verify this. So this is the exercise. So in general, what happens is when a set is acted upon a group, in general it need not be transitive, but you can always decompose X into space of orbits. Okay, so first of all, GBA group acting on X. First, we will consider X in X and note that OX, the orbit of X, we can identify with the coset space with G mod GX. So the map is take any coset GX, you send X to G comma. Okay. So this way you get a map and you can identify OX. We see that we get a bijection, this map. The row map gives us a bijection from G of GX to the orbit of X. And also you can ask if Y belongs to OX. You also have GY. What is it? Then there is relation between subgroups. GX and GY and orbits OX and so the thing is you can check that it is easy to check verify that OX equal to OY and GX and GY are conjugate. Okay. Subgroups of G. In other words, if they take note that if Y belongs to OX, then by definition, then there exists a G in G. G times X is equal to Y. Okay. So then the claim is that GY claim GY is equal to G inverse G GX G inverse. It's conjugate to that. Okay. Thus, if you take any element here, the conjugate, this consists of all G H G inverse H is in GX. So if H is a group, then its conjugate by an element of the group is again a subgroup. Okay? If H is a subgroup of a group G, then the conjugate by an element of that subgroup is again a subgroup. So, and the claim is that these two are related like this. This is because note that if T belongs to G, Gx, G inverse, then T is of the form G, H, G inverse for some H in Gx. Okay. So now T times Y is equal to G times GH inverse, because T is that element, acted upon Y, but Y is GH G inverse Y. Y is, I know that it is of the form G times H. So now I can apply G inverse on that. So what I get is G inverse. I can take it together and I get identity. So what I get is G H G inverse G spread on X. Okay. But G inverse G is identity. So what do I get is this equal to G H X, but Hx, because H is in Gx, so that means H times X is X. So G times X is equal to 1. So this implies T belongs to Gy. So that is what we have shown is Gx G inverse is contained in Gy. So other way equality also easy to prove. You take an element in Gy and you can produce an element, because y is of the form gy, you will see that you can find an element in h in gx. Any element in gy can be written as g h g inverse. Okay, so I will leave it as an exercise. Check this. Gy is contained in, with the assumptions on x and y, gy is contained in gx g inverse. Okay. Yeah. Okay. So this is what we are going to get between these two elements. So in other words, so for example, a GPA group then we can define an action. Last time I defined one action, but this time I will define some different action. Action G on G as follows. G cross, so I want to define action of G on G. So that means I have to have a map from G cross G to G. So what is the map? Take G and take any element G1. So I want to know what G does to this element G1. So I will take G, G1, G inverse. So that is G acts on itself by conjugation. Okay. So if G is abelian, then this action is trivial. So what is the meaning of that? So G2, I have this action, this means I have a homomorphism, that is the induce the group G acts on itself like this thing. So if G is abelian, I want to say that the conjugation action of G on itself is trivial. So what is the meaning of a trivial action? Action is said to be action. The action of a group G on a set x said to be trivial if d dot x equal to x for all g in G and for all x in X. That is equivalently the induced homomorphism rho from G2 bijections of X. This is set of all F X to X. F is a bijection. Last time I mentioned that giving a action is equivalent to giving a homomorphism. So that means given any action, I will always get a homomorphism from G to the set of bijections. And conversely, if I have a homomorphism, I get an action of G on the set X. Okay, that's what I said. So that's the meaning. What I means is I have given an action. So that means I have a homomorphism from G to the bijections of X. So this is trivial. That is, rho of G is equal to the identity of X. This bijection for every G, for all G. So this is, we say that action is trivial if such a thing happens. Okay. So what we are saying that if G is an abelian group, okay, so then the conjugation action is G acting on itself by conjugation is a trivial action. That means because G1 G inverse is G1 for all G in G and G1 in G. If G is abelian, because it commutes, no? Any two elements commute, so you will see that it's the corresponding action is trivial action. Okay, so this is what we get. Okay. So in this case, look at, so what are the orbits in this case? So if G is acting trivially on X, then OX equal to set OX. The orbit of X is the singleton for all X in X. And Gx is equal to G for all X in X. So this is the equivalent condition that G is acting trivially means that the orbits are singletons for all X in X and the stabilizers are the whole group G itself. Okay, so this is what the action means. Okay? So in general, it may not happen like this. So for example, if G has more than an element, so in this case G for this action, you will see that there are as many orbits as the elements of X. Okay, if G is acting trivially on a set X. Okay, if X has more than one element, then the number of orbits equal to the cardinality of the set X. So this is generalities. Okay, so let's use this to prove some results. Okay. Let G be a prime number and G be a group of order e power n for some n greater than 21. That is, the cardinality of G is e power n. That's what we are mentioning. So then what we want to prove some non-trivial result about the group G, once it has cardinality some prime power, then we want to derive some non-trivial results about the group G using the group action. Okay? So for that, what I consider is note that if H contained in X, if contained in G is a subgroup, then the order of H and this, I assume proper subgroup, order of H and order of G mod H. See, order of the group always divides the order of the subgroup always divides the order of the group. So that means order of H is some p power m for some m less than n. So, and once you have that, then the quotient G mod H is are also of order p power m and p power n minus m for some m 0 less than equal to m. So 0 less than equal to m. So this can be any of this thing. Okay, order can be always p power m and p power n minus m for some. So if I always have this, okay, so that means now if G acts on itself by conjugation and consider CG the subgroup consists of G in G like that G H G inverse H for all H in G. So this is called the center of. To note that identity element is there, it satisfies this property, and if two elements satisfies, then product also satisfies. So G belongs to CG implies G inverse belongs to CG. Because if you look at this equation, G inverse equal to H for all H in G, we'll also say that if I apply G inverse on the left hand side and G on the right hand side, I'll get H equal to G inverse H G. So that is same thing as saying that G inverse is in the center. This is called the center of G. Okay. So if G is in there, G inverse is also there, and if G1, G2 belongs to CG, implies G1 dot G2 this also is in CG. In other words, center of G is a subgroup of G. If G is abelian, then center of G is the whole group itself. Okay? Otherwise, it will be a proper subgroup. So this is if and only if you can say that center is the whole group, if and only if G is abelian. Okay. So now what we want to show is that using the action of G on itself by conjugation, we want to say that you start with any group whose order is a prime power, then the center is non-trivial. That's what we want to do. Okay? So first, before going further, I will say that if G is a group, is a finite group acting on a finite set, then we can set X, finite set X, then we can write, then we can write X as disjoint union of orbits of X for some X orbit X in X. Okay? So that means X varies over some collection of subsets of X, so that I can write, take orbit of X and orbit of Y. Y is another element. The intersection is disjoint. So what I'm saying that if OX intersection OY is not empty, implies OX equal to. So we can select representative in this in such a way that these are all disjoint. This X can be written disjoint. Okay. This is easy to prove from the fact that I have mentioned earlier, that if you take any element in OX, its orbit is same thing as that of X. So that means OX equal to OY. So similarly, if it's in the intersection means, so Z is in OX and also OY, you say that OX equal to OZ and also equal to OY. So that means, so if Z belongs to X intersection OY, then OZ, OX equal to OZ, and this also equal to OY. So that will say that OX equal to OY. So that's the argument that I had mentioned earlier. So I can write any, if a group is acting on this thing, so then I can always write in this form. That's what we are saying. Okay? Yeah. So now consider G, the group of order P power n, where P is a prime number. N is some integer greater than. So then what we want to show is that the center of G, then CG is equal to, is not equal to the trivial group. That is, center of CG is a non-trivial subgroup of G. That's what we want to claim that. So this is because what we are saying is, now look at the action of G under the conjugation action. Action of G on itself. So I can express G as disjoint union of the orbits of G. G belongs to some subset. Yes, this is a subset of G. Okay, and among this we'll also have, so this is, I can write it as this equal to, note that every element of the center is a singleton set. So it is CG disjoint union OG1 disjoint union OGK. Okay. So now look at this. What we get is P power n is equal to, because the cardinality of the group is P power n, is equal to cardinality of G, cardinality of the center, plus cardinality of OG1 plus etc. The cardinality of OG. Okay. Note that cardinality of OG1 etc. Cardinality of OG. Okay. Okay, so first let me assume that so if G is abelian or commutative, then G equal to CG. Okay. So it is concept of singletons in that case. So and whatever we wanted to do is already clear, because what we are in that case CG equal to G. So that means it's a not a trivial group. It's not the identity group. That's what we have shown. Okay. So assume that G is not trivial, not abelian. If G is not abelian, then what we get is P power m is equal to CG, and look at the cardinality of OG1, etc., cardinality of OGK. So on this cardinality of OG1, etc., cardinality of OGK are divisible by P. So that implies, because P power m I am expressing as cardinality of CG plus cardinality of the orbit of G1, orbit of GK, because each one of them I can identify with the quotient group of G. So hence the cardinality will be divisible by P. Okay. So this will imply that cardinality of CG, P divides the cardinality of CG. Okay. And cardinality of CG is non-zero, because since cardinality of CG greater than or equal to 1 implies that CG is not E. If it is E, then cardinality is 1, then P cannot divide 1. Okay, so that will say that CG is non-trivial. Okay, so just by looking at the action, we can conclude that if you have a group whose order is P power n, then it will always have an element which commutes with, always have an element which is non-trivial and which commutes with every other element of the group G. So that's what we get here. Okay. So this one application of group action. So I want to derive some more application. So I'll just introduce some notation and I will prove it next time. So let me just do that. So in Professor Raghavan's lecture, he was considering abelian groups. So I will consider some special kind of abelian groups. Okay, let P be a prime number. And n greater than or equal to 1 be a integer. Consider the group Z mod Pz cross Z mod Pz n times. So this is usually denoted by Z mod P Z power n. This is the definition of this is just this. Okay. So now, given that, and assume that n is, so let R be an integer satisfying 0 less than or equal to 1 less than or equal to R less than n. Okay. So, and consider set S equal to m. M is contained in, so I will write SR, contains Z power n, Z power n. M is a subgroup. And M is isomorphic to Z power P power R. So I want to know what is the cardinality of this set of all such gaps. So we find cardinality of SR. So that means how many subgroups of order P power R are there in the group Z mod P Z power n, where R is less than or equal to n. Okay. So for example, if R equal to n, then there is only one SR equal to singleton, and the cardinality of SR is 1 as M is equal to Z power P power. So if you have a subgroup, okay, of Z mod P power L, okay, Z mod P Z to the power L, whose cardinality is P power N, then it is exactly there's only one subgroup, namely the group itself, because the cardinality of the subgroup is same thing as the cardinality of the group. So hence it is that subgroup itself. Okay. So, and what is the cardinality of S1? What is the cardinality of this? So I mean that cardinality of this is e power n minus 1 by S1. So anyway, I will say how to compute these things and other details in the next class. So, for example, I just look at one small example here. Namely, I will specialize the case. Let p equal to 2 and n equal to 3. So then what I'm looking at is z mod 2z power 2. And I'm looking at the set m, S1, this set of m contained in z mod 2z 2, that m is a subgroup is of order 2, means m is isomorphic to z mod 2z. Isomorphism as a subgroup. So that means I'm not considering any set. I'm only considering subgroups. Okay. So special property. So if I consider sets of cardinality 2, there will be plenty of them. Namely, this has, so what I was saying is that it is the number of this thing is 2 power 2 cube minus 1 by 2 minus 1. So this is same thing as 2 cube is 8 minus 1. So it is 7. Okay. So that means if you take any non-zero element in this z mod 2z, okay, it gives rise to a subgroup. This thing. Because what happens is if I take any ABC belongs to z mod 2z 2, okay, and ABC is non-zero, not equal to 0, 0, 0, then look at the subgroup 0, 0, 0, and A, B, C. I'm saying that this is a subgroup of Z mod 2Z and it's isomorphic to Z mod 2Z. So any non-zero element will give rise to such a subgroup, because what happens is A, B, C, if I add it in this group structure with A, B, C, what do we get is 0, 0, 0. So that means this is a group with one non-trivial element whose square means in the addition language is twice that element is 0. Square is trivial, so that is same thing as saying that twice that element is trivial. Okay? So this way so this is what I claimed there. So let's look at here. So P minus 1, P is 2 for me, N is 3. Okay, so that is 2 cube minus 1, so 7. P minus 1, P minus 1, P is 2, so 2 minus 1 is 1. So the cardinality of the set is S1 in this case. Okay, S1 I should have written corresponding to 2. Okay, the prime number 2. So also I should write here P. It depends on P. Okay, what P I am doing. Yeah, so in this case it's very easy, by hand you can compute. Okay, but in general you want to answer this question: what is the cardinality of SRP? Okay, so it is to just counting like the way we have counted is quite cumbersome. Using the group actions, you can count it easily. That's what I want to establish in the next lecture. So, and you can, once you use the group language and count it, use the group action, you can count the cardinality of this easily. That's what I want to explain in the next lecture. So with this, I will stop.